Very good evening to all of you. I warmly welcome you all to The Blessing of High Dimensionality, a random matrix theory perspective, the third webinar of the educational webinar series M Talks, organized by the Mathematics Society of University of Moratuwa. I am sure all of you will enthusiastically participate and have a fruitful session. Before starting the session, I would like to kindly request to mute your microphones so we have a smooth flow. Also, you can use the chat to raise your questions and we will address them in the Q&A session. Without a further ado, let's get to know about this astounding individual who will be our guest speaker for the day. He is a distinguished alumnus of University of Moratuwa. Currently, he serves as a senior lecturer in the Department of Electronics and Telecommunication Engineering of University of Moratuwa. Ladies and gentlemen, please welcome our guest speaker for the day, Dr. Prathapasinghe Dharmawansa. Sir, it is an honor to have you here. Over to you.
Thank you very much, Eshani, and thank you very much, Dr. Bimali, for giving such an interesting introduction to my career and myself. Hi guys, everybody. Good afternoon and good evening at the same time. I hope you guys are doing well amidst this pandemic situation. Let me go ahead and share my screen with you. Let's see how to share. Here we go. Share. Okay, can you see my screen though? Can somebody say yes or no?
Yes, sir, we can see.
Okay, great. So let me go full screen now. And here we go. Okay, first and foremost, I should extend my sincere gratitude for the Mathematics Club Society, in fact, actually, for inviting me to give this talk. I'm going to talk about the blessings of high dimensionality, a random matrix theory perspective. This talk is going to be, first part is not going to be pretty much technical, but latter part is going to be somewhat technical. So I spent some time to make the slides fairly accessible. You will see how as we move on, actually. So I know very little about this subject. So I thought to put this slide in the beginning. This is an iceberg. Typically, we know that an iceberg, the part portrayed out from the sea is small, but yet underneath, there's a massive part. Today's talk amounts to scratching the tip of this iceberg. If you think about random matrices, random matrix theory as a massive iceberg. So I know very little about the subject, but I have been conducting research in this subject for nearly a decade. So I'm going to share my knowledge with you in the next 1 hour or so. So let's move on. I'll start with a few motivational examples. This is an image taken by myself back when I was in Finland, Helsinki, the capital of Finland, 2012 summer. So these red flowers are tulip, whereas these yellow flowers are daffodils. So you can see this image is crystal clear, at least to me on my screen. Natural arising problem is image noise, actually. So I simply added a bit of noise to this image. You can see this is the original image. Now, this is basically the noise image. So when I say I add a little bit of noise, it doesn't make much of sense because those who are really technical, tech-savvy people think, what kind of nonsense you're doing? You can't add a bit of noise. Yes, this is like I added some AWGN noise with certain variance, certain covariance metrics in more advanced terms. Okay, so then among so many tools that people use to denoise these images, one of the most important tools is basically singular value decomposition. So I did a little bit of mathematics using MATLAB and then did some singular value decomposition, and then you can see I recovered this image. Now, if you go back, this is noise image. So I could recover this image using singular values like this. Of course, it's still noisy. I could not remove noise, but it's like a noise reduction happened. Now, when I talk about an image, actually, the image is nothing but an array of numbers. Actually, it's basically an array of numbers. And you can see somehow the notion of matrices comes into picture right now. Now, moving on to the second example, though, this is about pretty much celebrated model, linear model. or in statisticians, they call it linear regression, multiple linear regression they call it, or in machine learning they use linear model, and so many sciences they use linear model. The idea is like you have a certain response variable and there are certain features or covariates or design variables, whatever you call it. So the basic idea is you try to find a linear relationship between the output and input cycle, a really linear relationship. Now, in this particular example, though, I took from one of the most famous books in statistical learning theory written by James Garrett, Daniel Aviton, Robert Tibshirani, and Trevor Hesty. The latter two guys are from Stanford Statistics. The idea is like you regress sales with some sort of a TV advertising cost and radio advertising cost. Now you can see these small red circles. They represent the true observed values. And this very beautiful plane is basically a linear regression fit, Basically, you are going to fit line to this data set. Now, you can immediately see when you fit a line to this data set, though, you can see some small red circle protrude out from this data set. That is because they don't follow this plane or basically line. There's no linear relationship. So technically, we call them residuals. You can see certain amount of matrices will come into picture actually, and these protrude out portions are basically errors or residuals. Now you can see linear model, very famous linear model. It also has certain amount of randomness and vectors, matrices. Now this is very interesting. Detection and estimation theory, one of the most advanced theories in the statistical signal processing. So detection and estimation part. Now you can see these are fighter jets and they go here, they go there in no time critical applications they are doing. They want to find enemy targets and they don't want to be seen by enemies. So the paramount important topic or thing here is basically to focus on detection and estimation. When it comes to the very core fundamental problems of detection and estimation theory, which is largely discussed in statistical communication theory, though, we talk about observed variables, observations, which are noisy observations from targets, and then you want to filter out somehow or the other using some sort of signal processing advanced algorithms to make sure that whether desired signal is there or not. Actually, you are cherry picking. Actually, you are supposed to be doing cherry picking. It's a pretty hard thing actually. So you can see these systems work. This advanced weapon system works thanks to advanced signal processing algorithms, which encompasses all this matrix method. And last but not least, actually, 5G networks. 5G is a set of technologies that people put forward recently to increase the throughput of wireless communication so that using your mobile devices or your vehicles or whatever, you can have end-to-end seamless connection. Actually. Now, when we talk about 5G networks and 5G technologies, the underpinning technical details will have massive MIMO. That means basically multiple input, multiple output antenna system where our transmitter and receivers are typically equipped with multiple antennas. In that case, actually, the channel is going to be like a Gaussian matrices will come into play actually. And you can see on top, when you look at the technologies, you can see very beautiful figures like this, very beautiful, very fancy figures and things are moving here and there. But if you go deeper into the technology, you can easily see the technology consists of small bits and pieces of fundamental blocks. These most fundamental blocks are due to random matrices or matrix observations and things like that. Now, what's the most important and most common feature to all this example that I already put forward is very simple actually, surprisingly simple thing. Observation, what you observe in your word, signal, which is you want to see, Unfortunately, you are not going to see because unwanted noise is there. So it's a unified view is image, observation is image, is original image plus contaminated noise. This is very simple linear equation, It's an additive noise, not multiplicative, but additive noise. It's extremely simple actually. Now, if you a little bit move forward, you can see an array view. Observations consist of an array. I mean, you can write it as an array matrix, and the signal is a matrix. So noise is also a matrix again. So when you add deterministic parts, the signal is deterministic. To a random part though, the composite is going to be random. Okay, so signal is deterministic, may or may not be deterministic, but for the time being, if you assume it to be deterministic though, once you add noise, which is inherently random, noise is going to be random unless somebody purposely make it, it's going to be random. So when you add random thing to deterministic thing, the observation is going to be random. Now, you have a problem actually. When you have random things, how would you detect a signal using noisy observation? This is at the core of all signal processing algorithms. No matter how they do, what they do actually, what they're going to do, that is at the heart of all signal processing algorithms. Okay. Now let's see an example of this randomness. This is called Bernoulli site percolation. Percolation is basically end-to-end connectivity, I would say, in very layman words. So this is a square grid is there, as you may see. And the square grid with probability P, I put green dot, and with probability 1 minus P, I put red dot actually. Now P is a very low value here. Because of that, there are so many red dots. But then what I'm going to do is like, I'm going to keep increasing actually P value, probability value from 0.001 to not 1, basically 0.9 value. So let's see what happened. You can see now, little by little, green blocks start to dominate, and it moves, and it moves. And at some point, actually, you can easily find end-to-end connectivity. We call it percolation cluster appears. Now it stops, pretty high probability now. So P is pretty large, of course, less than 1. Now you can see, you can easily go through through all these hurdles, green, red blocks, and reach the end actually. So this is called a Bernoulli site percolation. There's another one called bond percolation. This is these things are studied related to lattices actually, which we should not go into much detail. But here you can see what I have done is like I changed the probability. I changed the probability of occurrence of this green and red blocks, and then I start with very low probability. That means reds were dominating, and then I move forward slowly, and then we have seen actually witnessed that. In the beginning, though, you could not go from here to here, this corner to this corner, whereas after some time, actually, you could see a path, a continuous path from here to here. So it's called a percolation cluster appears actually. Now, this is not a random thing actually. This is basic idea. The mathematical details are there. So you create a square matrix n by n. So each variable is chosen from Bernoulli trial. That means either 0, 1, it can occur. If it is 0, it's like a red. If it is 1, it's green. That's it. So there's a critical probability though, when you increase P though, there's a critical probability below which no percolation cluster appears, above which the percolation cluster appears. So this critical probability in physics, they call it phase transition phenomena. Phase transition, that means phase transit from no percolation to yes percolation, no percolation cluster is going to appear. Now you can see the probability when you fix the dimensionality, when you vary the probability of occurrence actually, this kind of interesting thing can happen. Now let's see what if you keep the probability like fixed, but you change the dimensionality, which is the theme of today's talk. What will happen? Now, what do we talk about large n behavior, and why do we care? So some people say the bigger the better. Let's go ahead and see whether the bigger the better or not. So why do you care about bigger systems or bigger things? And you can see in day-to-day life now you are working with complex systems. So if you look at your social networks, I mean, you are networked with so many people, and they are networked with so many people. And if you try to plot them like a graph structure, though, you can see the complex system tend to appear. If you want to find the dynamics of complex system, so there are many constituents actually. So there are many variables actually. These variables interact with each other in more non-trivial fashion. So now if you try to understand this, you can see you are going to deal with so many variables, or random variables, or parameters, or whatever you call it actually. Now, to understand this thing in more toy fashion, or at least like try to get some insights into this problem. So we do go back to one-dimensional example actually. So this is a classical random sum. So you choose x1 up to xn IID random variables, well xk basically xn, and each is having mean 0 and variance 1. This is very simple. And then you consider the sequence of S1 up to Sn. So Sn is basically sum. We call it like a sample mean if you want. Now, if you look at careful right-hand side, this bracket, you can see when n equals 1, it is x1. When n equals 2, take the mean of 2 variable. When it is 3, like you divide by 3, and so on and so forth. Now you can see, should x have some distribution? So if you add 2 random variables, more or less, you violate the distribution, unless it's Gaussian. So if you add 2 Gaussian random variables, of course, they're going to be Gaussian. But if not, you start with 1 random variable. So you add 2, you add 3. As you move on, actually, the shape of the distribution or the probability measure, it's going to get changed. Now the problem comes like, okay, Now, do you have any hope as n moves to infinity? Do you have any hope that this become random measure become non-random measure? Because this is random, like when you add 2, it becomes one shape, 3, another shape, and so on. So shape is getting changed rapidly over n, within. So now the question is like, but will you be able to see a hope here? Like, okay, after this thing, this converges in some sense. You may not be able to understand what is the meaning of convergence for random sequence, but don't worry. But do you think that something will happen? Well, you can run a small simulation, very simple. This basically, I get a uniform random variable, and then you keep adding the uniform random variable. Let's see what happens. You add 2, it's become triangle and keep changing shape, keep changing shape, keep changing shape, keep changing shape. Alas, what's going to happen? Ultimately, it looks as if it was Gaussian. It looks as if it was Gaussian. Well, it is also not surprised. This is known as central limit theorem. More formally, we call that the probably scaled scale sample mean, scale by square root of n. In distribution, it converges to standard normal random variable in distribution. Okay, in distribution, it converges to standard normal random variable. Now, you must have seen convergence in like deterministic sequences. There are ratio root test, and so on and so forth. But this is actually stochastic convergence. These sequences, you can see like S1, S2, S3, they are completely different probability measures actually. I mean, S2 looks like a triangle, you know that. S3 doesn't look like a triangle, and so on and so forth. But it turns out that when n is pretty large enough, this goes to standard normal random variable. But it doesn't mean this random variable become Gaussian though. This is the formal definition if you really want, but don't worry too much about that. This is a formal definition actually. The probability density is the cumulative distribution function actually converge to cumulative distribution function of standard normal Gaussian actually. This is the basic idea. Right, this is a bit technical. Anyway, so there are other stronger forms that call almost sure convergence and improbability. These are very strong actually. Almost sure is stronger than this one, and this is most weakest one actually. Okay, now you can see if you take in one dimension actually, when you increase, when the system is getting larger and larger, so you have a certain hope that this at least sample mean is that not going to go here and there. It doesn't oscillate here and there. The oscillation ceases and it goes to a non-random measure actually. The measure is like Gaussian. So we don't care. We are very happy actually because bigger the better now. Now the next question is, can you see the same analogy among random matrices? In random matrices, can you see the same analogy? The answer is yes, you can. Here we go. We define random matrix as a matrix with elements are drawn from certain probability measure or certain probability distribution in your language. Say for instance here x1, xnn, there are n square variables here. So you draw xij from either normal, standard normal, or Bernoulli with P, or any other uniform distribution. Doesn't really matter actually. Doesn't really matter. We just draw random variables like this, and we just populate this matrix. And since this is a square matrix, you can always talk about eigenvalues. So what's the meaning of eigenvalues? Well, eigenvalues is basically you solve this characteristic equation. Determinant of x, this is a normalized one, square root of n minus lambda. You solve this equation. This is basically nth order polynomial. Since this is these are real symmetric, imagine these are real and symmetric metrics, then we know from theory that the eigenvalues are going to be real if it is symmetric. If it is not symmetric, they are not going to be real, but complex numbers, complex eigenvalues occur in conjugate pairs. I mean, these are well-known things. Now let's try to see if you get this kind of random matrix and try to calculate the eigenvalue, so eigenspectrum, and normalize, and then see what will happen. So this is one of the most interesting examples. This is called Wigner's semicircle law, invented by Wigner back in 1955. Wigner was a physicist, theoretical physicist. He was studying the energy levels in heavy nuclei, and then he found that there are so many energy levels, and they wanted to write so-called in quantum mechanics, people use Hamiltonians, and the Hamiltonians were like extraordinarily complicated. So he didn't want to write this. He was in a view that look, we don't wanna identify each and every particle behavior. We don't wanna identify because there are so many particles there. Instead, what we are going to do is the energy levels. We believe that they are derived from the eigenvalues from certain matrix ensembles. Certain matrix ensembles. So he went ahead with his idea. He took anyway Wigner ensemble basically symmetric Gaussian, and then he predicted the behavior of heavy nuclei interactions and everything using the eigenvalues. I mean, this is a remarkable discovery. And as a byproduct, he found this so-called Wigner semicircle law. In a sense, it shows that if you populate your previous matrix, this one, make it symmetric. That means top half and bottom half around diagonal are the same entries, and each with any distribution. Doesn't really matter what distribution is. You want to make sure that distribution has mean 0 and variance 1. Okay, technically the mean 0 and variance 1, and then you scale it, and then you plot the eigenvalues. Then you plot the eigenvalues. We call it empirical spectral density. And then let's see what happens. Now you start with small values, like any smaller value, 5, 10, 20, 30, 40, 50. When n is getting larger and larger, you can see what's going to happen. So you can see small values and getting larger and larger, larger and larger. Aha, it's interesting, right? It's called Wigner's semicircle law. So it doesn't really matter what the probability measure that you start with. It doesn't really matter. You must have started Gaussian. You must have started with Bernoulli or something else, some weird distribution. Doesn't really matter. Doesn't really matter as long as mean 0 and variance 1 with certain moments restrictions are there. These are subtle technical details. But at the end of the day, so irrespective of your initial probability distribution or probability measure, the empirical spectral density function is empirical spectral density actually converges to this semicircle. It was a surprising result anyway. Now let's see another surprising result. This is called Gerco's full circle law actually. It's very simple. You go back to this model. You make all the entries real, not symmetric at all, just real entries. And we know that eigenvalues should occur in conjugate pairs if they are complex, otherwise they are going to be real. And then you plot it, simply plot it. Okay, simply plot it. Let's see what happens. You start with a very small value, and then you keep increasing the dimensionality of the matrix and see what's going to happen to all these eigenvalues. So I'm going to plot these eigenvalues on a complex plane. This is right. There are two axes actually, but somehow something is missing somehow. I'm sorry for that. Let's let it run. You can see as n grows larger and larger. Aha, it's interesting, isn't it? Now, when you start with, so let me start from here. Like you start with very small values, 5, 6, 7. You can see eigenvalues are wiggling actually. They are wiggling. And then the fluctuations tend to cease now. Fluctuations tend to cease and they tend to conglomerate. They tend to conglomerate into this unit disk actually. This is called full circle law actually. Or in other words, it is said that it's uniformly distributed over this unit disk. Okay. I mean, this is a surprising result. Why? Because you start with, again, you started arbitrary probability law measure, but then at the end of the day, it converges to the same unit disk. Now this is very useful because in day-to-day life applications, I mean, you may encounter different very complicated distribution. Even sometimes you don't know what the distribution is. But never mind. It says that you start with certain reasonable distribution. At the end of the day, when n is large enough, then it converges to this kind of stuff. So the question is like, is it an accident? Is it just a coincidence? I mean, 2 things coincided, 3 things, it happens 3 times, we call it a conspiracy. Or I mean, is it a coincidence? Or I can ask conspiracy. Or is asymptotic behavior of eigenvalues much robust? This is what Wigner identified actually. Well, in the modern probability theory and random matrix theory, this is known as universality. Universality in the sense, like in layman's language, irrespective of the probability distribution that you start with, the end result, so it's going to converge to the same stable density function actually. So that's the meaning of universality. I mean, layman's meaning. Okay. I mean, you can formalize using mathematics, but that's not the idea. So why do we care these things? Next question is, you may ask, I mean, okay, these things are very interesting mathematically, like 1960s. I mean, who cares? We are in 21st century. I mean, we don't care about this thing now, right? We have computers and everything. I mean, why don't you want to care this kind of seemingly old result? You are old and your theories are old. Well, let's see. Why do we care in this 21st century? Now, what happened in this century? In this century, willingly or unwillingly, you are part of massive data consumption network. You yourself produce data as well as you yourself create data. Every time you log on to internet, Google or whatever the internet portals and stuff like that, and you do something, you demand data. At the same time, those who are sitting behind you, the service providers and everybody, you are providing data to. So it's like exchanging process actually, data exchange. So willingly or unwillingly, you are filling your terabits of your hard disk with data. Sometimes you like this, sometimes you don't like, but as a matter of fact, you are afraid that something might get lost and you fill your disk with data. So now we have so much data, actually, unbelievable. So what are the data generation mechanisms now? DNA sequencing, internet portal, financial data, tick by tick financial data, a lot of high frequency trading, and satellite imagery, actually, because then you are talking about like very fine images, like it consists of so many pixels, and sensor networks, and in particular national security. They are looking at you. They are looking, big bosses looking at you. How are they going to look at you? Well, they can't see you. They don't have divine eyes. What they do is they use data. They use data to see what you are doing, what your motives are. They're going to data to estimate this. We are in an era where the number of samples probably of the same magnitude, order of magnitude as features. Now, when I say about data point, a person, actually, I would say, if you take a person, you can find several attributes to person, like height, weight, salary, gender, and so on and so forth. Like 10, 20 years ago, actually, if you look at data matrices are very tall, actually. That means very tall in the sense like so many rows, whereas a few columns, actually. But thanks to this modern data generating mechanism, data capturing mechanism, actually, what it did, basically it expands the horizon, and now some matrices are very fat. That means the number of data points is smaller than the feature, actually. The number of features can be pretty large in comparison to the data you have. So imagine a very simple example, like rare cancer. So you may find 5 to 10 people with that rare, or probably 5 people with rare cancer. But if you get a genome from them, you get hundreds of thousands of genomics data, actually. So you can imagine the data matrix to be very fat, in contrast to traditional data matrices, which are very tall, actually, slim and tall, in contrast fat. Or probably these two dimensions are comparable, actually. Now you can see, you are in an era, very strange place, actually. Now you are in this, our human civilization is there, now stuck at some point, actually. You can see from this diagram. Back then, P is much less than N, classical statistic though. Now P is much greater than N, or P and order are of the same order of magnitude. Okay, P and N are of the same order of magnitude. So we write simply P proportional to N. This is a way of writing. Now, when P is greater than N, actually, most of the statistical procedures established, or you must have learned so far in your high schools or in your university level, or you are being taught at the moment, they tend to fail, actually. The primary assumption of these all things are basically is a P is much less than N, or at least P equals N. Now, in this era, now P is greater than N, now P proportional to N. Now you can see how relevant that previous mathematics, the theories that developed previous people like 10, 15, 20, 30, 40 years ago, how relevant are they in our modern context, actually. Okay, so there are new challenges appears. Say for instance, we call classical asymptotic fails. Okay, that means inconsistency of principal component analysis. In a short while, you are going to see it. And the new phenomena, new opportunities occurs, actually. We call it a phase transition in PC. Example, like one example, new phenomena, I said there are several things. Out of these several things, actually, one of the most important things from signal detection point of view, signal processing point of view, is phase transition in PCA. Okay, so in a short while, you are going to see very nicely the basic idea behind it. Now you can see we are in an era now, or we are moving into an era where P is much greater than P is proportional to N, in which actually typically traditional statistical methods, quite traditional statistical methods, tend to fail. But it doesn't mean that's the end of statistics. No, they discover new things. They go for new procedures. They go for new theories. They do new research, actually. As a result, actually, the relevance of these old theories become very timely relevance is there, very importance is there, and day by day, actually, they are gathering momentum, actually, applicability of these theories. Now, let's see one of these results from 1960s. So pretty old result, okay? Pretty old, become more than 5 decades old, okay? More than 5 decades, no, 6 decades old, actually, right? 6 decades old, okay? Now, this is about Marchenko Pastcholo. It was quite famous. They were like Ukrainian mathematicians, probabilist, I suppose. What they were doing is like you get a matrix X. Again, since the universality is there, you choose X to be independent entries, but with any probability measure or probability distribution. We don't pay much attention to that. And then your idea is you create this X transpose X. We call it Graham matrix, or those who are familiar with statistics, this is sample covariance matrix, if you want. That's why the beauty comes from here. Actually, X transpose X is like at those days is like a mathematical object, but modern days, from the statistical point of view, this is basically sample covariance matrix. Here we go. And then they were talking about the empirical spectral density function that you define using this delta measure. What will happen? What will happen when you scale n and p? When you scale n and p, you push n and p to infinity parallel, such a manner that p of n ratio is fixed. Okay, that means like if you fix the ratio 1/4, so when p is 100, n is going to be 400. If p is 1000, n is going to be 4000. If p is million, n is going to be 4 million. So you make sure that you go to n and p go to infinity at the same rate, actually, at the same rate. Okay. So then you look at this empirical spectral motion. Now, surprising result appear. This is called Marchenko-Pasteur law, 1967. These are the mathematicians or probabilists. Now you can see that you find this this measure, though, this is a probability measure on probability. May not be able to understand, but that's how it is. This is probabilistic. The probabilistic nature, the random nature of these measures tend to cease, and it takes this very beautiful. It has this distribution, and it's called Marchenko-Pasteur law. The theory says that X, it doesn't have to be complex, it can be PNB IID entries with zero mean and unit variance. As n and p goes to infinity, n and p go to infinity, such a manner that p over n goes to gamma, a factor which is free of p and n. It's just basically a factor. In between 0 and 1, just to make sure that's pretty easy. It can be greater than 1, the original, yeah, it can be greater than 1 actually, according to the original theory, but I just simplified it actually, this one. So it says that it goes to this distribution. I mean, it's hard to believe. Let's do an experiment. So I just take this empirical spectral density. I'm going to calculate, starting with, say, certain ratio, like this is, I believe is 3/7 or 4/7, I believe. It's like 4,000, 7,000, 4 million, 7 million, and so on and so forth. So you keep increasing such a manner. You keep increasing in such a manner that P O and gamma is a constant. Now let's see what happens. You can see it started small early. You can't see anything. It's pure random, pure random. Now a pattern tend to appear. Now you can see. Now you can see what happened. This is the distribution that they found here. Okay. The equation of this one, these people found here. Okay. Again, I'm playing it. You can see in the beginning, you can't see it's chaotic. It's random. Measure is going to be random. But then random measure is going to lose its randomness and goes to non-probability measure is given by Marchenko-Pasteur. I mean, now you can see the theories developed in 60s. In the 60s, actually, are going to be instrumental in looking forward to, instrumental in modern context, actually. Like if you are looking forward into the next era, actually, these theories and these all theories are going to be paramount importance. Actually. Now let's see, like I have been, okay, so another one. So this is the theoretical distribution. You can see when gamma in between 0 and 1, and now I'm changing gamma values actually. In between 0 and 1, I change gamma values, okay, fixed. So I'm changing gamma values. So when gamma is nearly 0, the matrix, the eigenvalues are very concentrated, pretty much concentrated around this area. Now let's change gamma. What happens? You can see more and more uncertainty grows, and when gamma evolves, that means if gamma 1 means basically P and N, they are of the same dimension. That means how rectangular the matrices are. If gamma 1, that means nearly they are square matrices actually. If the matrix is pretty much rectangular, the eigenvalues tend to concentrate somewhere. You can see density function is much concentrated. Whereas when it's going to be more and more square, they are going to spread along this direction, along this eigenvalues actually. It's going to spread actually. Okay, much concentrated here, whereas this is much spread over some values. Okay. So that's also another point. And then moving into the utility of these things. I mean, somebody might ask them, okay, what are the utilities? I mean, why do you care about this thing? Okay, you say this apply here, there. Can you give some concrete examples in the sense like concrete areas there? Here we go. You can see there are a wide array of applications here. Applications include information theory, signal processing, wireless communication, and multivariate analysis, number theory, combinatorics, numerical analysis, econometrics, and mathematical finance. So I have highlighted few areas that are of great importance to us right now. and we develop expertise in these areas. For instance, information theory, we have been working signal processing, wireless communication, bit of multivariate analysis, not much in numerical analysis, but bit of mathematical finance we are interested in right now. So you can see this is basically like the random matrix is not only it is important in its own right, but it has wide array of applications actually. Okay, wide array of sciences are used this thing. So you can see different perspectives. You can see the first one is from M.L. Mehta, quite classic books in random matrices about applications in physics. The second one is probabilistic. Third one is again log gases and random matrices. So he's gonna draw analogy between gases, ideal gases and random matrices actually. Coulomb fluid problem. This is very interesting. And then the last one is what is pretty much relevant to us is random matrix method for wireless communication. This Moratuwa is from France. He's heading a Huawei research lab in France. He's quite famous person in random matrices as well as wireless communication. There are people who are developing next algorithm for the next century actually. They are developing algorithms for the next cutting edge technologies actually, which are going to emerge. They definitely use random matrices and so these are from the horse's mouth. So let's see a few examples, few papers. This from transaction information theory. What they use random matrices, they spell it out. Random matrices, eigenvalues of Wishart random matrices. These are quite known people in the world in this area. A little bit more, Moratuwa, he wrote the first paper in MIMO capacity, quite well cited, thanks to him. Today, MIMO systems are working, 5G things are working, thanks to his seminal paper. And then Ralph Muller's random matrix model via antenna arrays. And not only that, you can see physics. This is class physics A, maths, mathematical in general lecture. So they use about random matrices. Now you can see random matrices are here, random matrices are there. Well, you can always find the flavor of random matrix in any signal processing problem, most of the time. I would say most of the time you can find. Now let's see the agenda of this talk actually. I already covered random matrices at a glance. Then we introduce a bit of classical random matrix ensembles. So what's the meaning of random matrices? And then we talk about some new results and conclusive remarks. So moving forward, the classical ensembles actually, we call them Gaussian orthogonal unitary. Orthogonal in the sense that it comes from real entries. We call it orthogonal. Typically unitary, we call it complex entries. So these are very quite famous Gaussian orthogonal, Jacobi orthogonal, Wishart, we call Laguier orthogonal unitary. So the person who introduced this subject largely is due to J.J. Wishart, 1928. He wrote his seminal paper on this Wishart distribution. And ever since, hundreds of thousands of researchers have ventured into this area and did fascinating discoveries during last couple of decades actually. Now, if you move forward, what a Wishart matrix is. So you must have heard this word Wishart, and I spell out several times Wishart, and you may consider what Wishart is. Now, well, Wishart is his name. It's a matrix in his name. Well, you think about data matrix, a matrix, you have n columns. You can imagine Pn matrix, which has n columns, and each column is, here I consider complex normal, P0 with certain covariance matrix. Okay, and moreover, all these columns are independent. These columns are independent, whereas rows of this matrix are correlated, and the row correlation is given by sigma. So this is the very basic construction of Wishart matrix. And then by definition, Wishart matrix is this XX Hermitian, XX transport if it was real. And as an outer product, you can write XJ, like a rank 1 summation, in rank 1 summation, you can write XJ Hermitian. You take one column, put n by P by 1, and then multiply by 1 by P. So P by 1, 1 by P makes rank 1 P by P matrix. So you add n rank 1 P by P matrices, n rank 1 P by P matrix. I mean, mathematically, you can show that probabilistically this is going to be full rank if n is greater than P or equal P is going to be full rank. And this one, since 1 up to xn are Gaussian distributed like this, when you put into this form, actually W is said to have complex Wishart distribution. We call it Wishart P degrees of freedom. That means the smaller dimension is P degrees of freedom. So dimension n, sorry, I made a mistake. The P is the dimensionality of the matrix, N is the degree of freedom, and sigma is the covariance. Actually. Now, when you talk about covariance matrix, actually covariance matrix P by P, typically they are positive definite matrices, at least positive semi-definite matrices. Now, how do you understand the covariance, effect of covariance? Well, you are not going to understand effect of covariance unless sigma is IP. We call it white Wishart. That means these columns are uncorrelated. These rows are uncorrelated. Or we can think about rank 1 perturbation of identity. That means some parts you have correlation, whereas some columns are not correlated. So this is for the sake of easiness to study, actually, for the sake of studying these things. So you only study the properties. Okay. Now you may wonder why you are talking about Wishart matrices. Probably they are mathematical objects. They are again important in their own right, but it's of little use to engineering. You can say, oh, engineering is nothing to do with this one. Engineering has nothing to do with this one. This is just mathematicians, crazy people do this thing. These are useless. Okay, let's see what's going to happen. This is a random signaling noise problem, classical problem in signal processing, classical problem engineering, signal processing. So you imagine that signal is being transmitted, SK, a random signal. And then you observe a noisy version of random signal. This V is supposed to be some sort of array vector or something like that. Doesn't really matter. Rho is the signal strength. Square root of rho given here. The rho is basically signal energy. Now, if you consider single observation though, RK can be written like this. So your signal multiplied by this array vector V and square root rho is a technical way, and plus additive Gaussian noise, actually additive white Gaussian noise. Now you can, thanks to modern sampling techniques, actually you can sample like so many samples. In general, you can take n samples, actually. Okay, so SK is supposed to be Gaussian for the sake of easiness, and V square is normalized, and NK is basically complex normal. Now signal detection problem amounts to this binary hypothesis testing problem, actually. But under H0, under null hypothesis, rho is 0. That means no signal exists, just noise. Under alternative though, rho exists. There's an unknown value. We don't know what the rho is. What rho is, we don't know. But if it is there, signal is there. Very simple logic. Okay. Now under null though, you can easily write RK under the null. RK is basically that means this is not there. NK properties will move forward. This is CNP, 0IP, that you can easily show. But under the alternative hypothesis though, if the signal is there, you can do a little bit of mathematics and show that it is basically complex normal P with zero mean, and the covariance matrix is changed. Now you can see, because of the existence of a signal, actually the covariance matrix change. Or in other words, eigenspectrum, if you consider this covariance matrix IP eigenspectrum, all eigenvalues are 1. Whereas if you consider eigenspectrum of this matrix, population covariance matrix though, the largest eigenvalue is 1 plus rho, whereas the other all eigenvalues are 1, actually. Now you can see if the signal is there, maximum eigenvalue, the maximum eigenvalue of population covariance matrix, which is I have calculated here, is 1 plus rho. Otherwise, it's going to be 1. So if you have access to population covariance matrix, signal detection problem amounts to checking the maximum eigenvalue. If it is greater than 1, then signal is there. If it is not, signal is not there. Very simple logic. Okay, very, very simple logic. This is called Roy's largest root test. It's a consequence of, statistically speaking, it's a consequence of one of the consequences of Roy's union intersection principle. Now, if you move forward, you can see in reality, covariance matrix is unknown. Nobody's going to give you this matrix. Nobody's going to give you this matrix. This is unknown. However, we have access to samples, so we can create so-called sample covariance matrix. We can create sample covariance matrix. This is sample covariance matrix. So we believe that sample covariance matrix act as a proxy to understand population covariance matrix. It's an assumption. It's an assumption. It's an assumption which is common to so many engineering, machine learning, engineering, many problems actually. So we formulate the so-called sample covariance matrix. And now under null hypothesis, sample covariance matrix properly scaled. This is Wishart matrix, you can easily see because original were Gaussian. And this is Wishart with covariance rank 1 perturb covariance cycle. Now you can see what the relevance of Wishart matrices are. It's extremely relevant actually. It's extremely relevant. Now we consider lambda max of R. So we believe that, I mean, we can see from this heuristics, we can see lambda max should have detection power. Okay, lambda max R therefore should have detection power. That means basically you should be able to find, you should be able to detect signal merely looking at lambda max of sample covariance matrix. Okay. Well, to understand lambda max, then you need to have eigenspectrum of this one. Okay, eigenspectrum of this one. Okay. Now, this is what happened. You can see now we have to go here. So the signal strength can be different signal strength can be there raw. Now you can see signal strength can be weak. There can be weak signal, there can be strong signal actually. Some signals are weaker than some other signals. So the desired signal may have weak level or may have very strong level, okay? The level, signal noise ratio, in other words, you may have smaller, like low signal noise ratio, or it may be very large signal noise ratio, okay? Now you may see though, when NNP fixed, when you change the signal noise ratio, what happened to this eigen spectrum? Look at carefully, watch carefully this thing, carefully enough, you may see one of the eigenvalue detach from this bulk and separate. He is going to separate from this bulk. You can see it's one of the fantastic observations. Yeah, here we go. Can you see this guy had escaped. Again, I'll go back. You can see everything is in the bulk, but one guy tend to escape. He escaped from the bulk actually. Now this is the maximum eigenvalue. The maximum eigenvalue depending on the signal strength. It may stay within the bulk, or it may escape from the bulk actually. Now there's a daunting task here. Now some points you have signal here, but maximum eigenvalue doesn't escape. But for some SNR values, maximum eigenvalue clearly separate from the bulk, whereas some SNR values actually maximum eigenvalue stays within the bulk, and by looking at the bulk spectrum, the noisy spectrum, you are not going to see whether signal is there or not. It's a crazy phenomena actually, okay? It's a crazy phenomena. But whereas for some SNR values, by looking at the spectrum, you can immediately say, oh my goodness, this guy is outside from the bulk, outside of the bulk. So that means, yes, there is a dominant signal. Yes, there is a dominant signal. Now, this is not a just observation. There's a formal theory behind it. This is called BBP phase transition, or Baik, Benarous, and Fishy phase transition, found in 2005. Very recent, well, not that recent, but not that, well, it's not that recent anyway, but not as the result I showed you back in 1960. So under another hypothesis, if you don't have signal, once you properly scale this lambda max, in distribution, it goes to Tracy-William law. I mean, this is a law. Don't worry about this certain distribution. But this guy showed that very interesting phenomena. Even when you have signal, that means non-zero rho, even when you have signal, look at here carefully, even when you have signal, rho is non-zero now. If it lies below a certain threshold value given by square root of gamma, still it goes to the same law. You can see here TW2, here TW2, same law. When you don't have signal and when you have signal, but it is weak enough, it goes to the same law. What does that mean? From statistical point of view, lambda max does not have statistical power. There is no discrimination power at all. Statistical power is zero. It's junk. It's basically junk, useless. Just statistics is useless actually. However, if rho SNR is above a certain threshold, or in other words, the signal is strong enough, and then you can see it escape from the bulk, and the limit is basically standard normal once you properly normalize. That means lambda max has power. But this is known as phase transition. So what you have seen here is phase transition. What I have done is I kept the dimensionality of N and P fixed, and I kept I changed this rho value actually. I change this rho value. So you start from rho smaller value and keep increasing. Okay, so you can see now the signal is there. Signal is somewhere here, but you can't see. Now it escapes. See, now you can clearly see using lambda max escape from this. Okay, so this is a very interesting phenomena. So you can see this is kind of a high dimensional nature. This is the nature in high dimension. This bizarre thing happens. So we can talk about this thing furthermore. Above phase transition, lambda max square root of n. I mean, you have seen the square root of n law earlier, right? When I was scaling that random sum, that sample mean, I scale using square root of n, and surprisingly it went to Gaussian, right? Surprisingly it went to Gaussian, but again here, maximum eigenvalue, after doing all sort of mathematics and all sort of complicated things, lambda max properly centered and scale in lower square root of root n, and it goes to again normal 0 1. Or in other words, you can approximately write lambda max like this. This goes stochastic approximation. I mean, deterministically you can write approximation, and stochastically you can write approximation. The difference is stochastic variable is approximated by another stochastic or random variable. Random variable is approximated by another random variable. Okay. Now you may wonder why do we care these things? I mean, okay. Now you know that the relevance of this thing into a signal detection problem, and this diagram or this simple thing explains what happened to the mean value. This is a mean value. So mean value is like this. This 1 plus rho is traditional asymptote, traditional value. If gamma is 0, that means n is pretty large. P is fixed, n is pretty large. That is classical asymptotic. In the classical asymptotic, you have large number of data points, whereas P is very small actually. And then P of n nearly goes to 0. When P of n nearly goes to 0, gamma goes to 0. When gamma is 0, 1 plus rho. This is the line that you are looking at. This blue line is the line that you are looking at. The mean value, the centered value of lambda max. However, when you have non-zero gamma value, you can see there's a gap between this 1 plus rho is the maximum eigenvalue of population covariance matrix. This is the maximum eigenvalue of sample covariance matrix, that like mean value of that. That you can see these two guys have a permanent gap. There's a permanent gap between these guys. That means this estimator lambda max estimator using sample covariance matrix is permanently biased actually, However, in the classical asymptotics, when n goes to infinity, P is fixed. Classical asymptotic did not find this gap because it goes to 0. Gap goes to 0, gamma goes to 0. So this lambda max was a consistent estimator. The maximum eigenvalue of sample covariance matrix was a consistent estimator for population covariance matrix. It turns out that in the high dimension, it fails, it collapses, and there's a permanent gap value or bias is there. Bias, that means inconsistent estimators. Okay. Now, principal component, what you are doing is you get sample covariance matrix and you try to find eigenvectors actually, eigenvectors and eigenvalues actually. Now, you can see if the dimensionality are getting larger and larger, some sense, this kind of phenomena will appear actually. So this is called phase transition. Again, if the signal is weak enough, even the presence of signal, if it is weak enough, then probably you are not going to detect. But if it is strong enough, then you are going to detect this is maximum eigenvalue. When somebody can ask, well, if it is weak enough, no point to find maximum eigenvalue. Yeah, it's no point. Then you go for linear functions of eigenvalues. Okay. Right. So this is about large dimension. Now the question is like how would you get this result from finite dimension to large dimension actually? So to understand this one, we need to know what Wishart matrix is. So this is a Wishart matrix. This is a probability density function given by beta w. Now you may wonder, wow, this is kind of complicated. Actually, it's not complicated. So probability density function is by construction is a scalar valued function. The function is scalar. Okay. The input is vectors or matrices, but the output is scalar. So this is the determinant is scalars, and when you get trace of a matrix, that means square matrix, that's a summation of diagonal elements. It's a scalar. So all these things together are scalar variables. Okay, but the difference is like you pass P by P matrix here, complex matrix or real matrix to this function, and output is going to be value, a single value. Okay. But then since W is Hermitian positive definite actually, so the number of degrees of parameter freedoms are going to be P plus 1 and here P square. Now you may wonder what this is. Well, it's very simple. If n equals 1, P equals 1, this is going to be chi square with n degrees of freedom real, chi square with 2n degrees of freedom if elements were complex actually. Well, probably you are not much familiar with this one, but this is bread and butter for many people in the world. Actually, if you are working signal processing, advanced signal processing era, this is like a bread and butter actually. Okay. And then eigenvalues. I mean, then if it is finite dimensional, but then can you talk about eigenvalues? The James, A.T. James, very famous statistician, he derived this joint eigenvalue density for real and complex. If beta 2 is complex, beta 1 is real. It's like this. Okay. So this is called Vandermonde determinant, quite famous Vandermonde determinant. And this is just a product. And this is the problematic guy. These are known as angular integrals. So DS we call Haar invariant measure over unitary group. So you are going to do this integration over unitary group. That means the group of unitary matrices form a group actually. Over that group actually normalize so that the total volume of that group is 1. So these are called angular integrals in physics. They have been evaluating these integrals for probably a couple of decades now. So there are different forms actually. So this is called angular integral actually. Now when lambda and sigma like kind of non-trivial matrices, you are not going to solve this integral in very simple form. However, when sigma is I actually, you can right away solve this integral and get this answer. It's fairly trivial because trace of H lambda H Hermitian is trace H Hermitian H lambda. H Hermitian H is I because it's from unitary manifold, and then trace of lambda. This integration variable has nothing to do with this, and you take it out. And if you integrate over your all unitary manifold, because it's normalized to 1, the answer is going to be 1. This is a probability measure as well. Okay, so this was solved 1939 actually. This was solved 1939, but sorry, I'll come to that one again. I'll come to this integral again. So if this variables are, if this sigma is uncorrelated, that means if sigma of the original Wishart matrix is IP, that means uncorrelated Gaussians in the original model, and then these eigenvalue distributions can be written like this actually. Now, why you call it Laguian ensemble and all sort of stuff? Because of this reason. So once you factorize like this WX has a Laguier weight actually. Wishart Laguier weight. The F matrices Jacobi weight, because Laguier polynomials are there, generalized Laguier polynomials. These are Jacobi polynomials and Gaussian ensemble related to Hermite polynomial. Hermite weight is, if you are aware of orthogonal polynomials, you know, orthogonal with respect to a certain weight function. And surprisingly, these weights appear here in these eigenvalues in joint eigenvalue distribution, thanks to sigma equals I actually, okay, sigma equals I, okay. But the question is, what if sigma is not I? Then this object is going to be pretty complicated. This is known as hypergeometric function of 2 matrix arguments. It's a very complicated combinatorial object. So it's like you integrate, this is called splitting formula. So you integrate hypergeometric function of 2 matrix argument, 1 matrix argument over this unitary manifold, and it's gonna, I mean, don't worry about that. And it can be expanded like this. It's extremely complicated. This zonal polynomials, parallelly discovered by James 61 and L.K. Hua, a famous Chinese person, a famous Chinese mathematician who never been to a university in his lifetime, but he analyzed, he was doing quite a lot of work in harmonic analysis, and part of his harmonic analysis, he discovered this zonal polynomials actually. So these zonal polynomials appear here. I mean, these are very cumbersome objects, you believe me or not. It's very difficult to work with them. But so you can see the complexity increases, 0 of 0. These are, so the complexity increases in the finite dimensional domain. So because of that, people tend to look at what if n goes to infinity, or n and p goes to high dimensional limit, what's going to happen? So you want to analyze this thing. You say, for instance, like say for instance, when you are working on certain problems, this pop up, and then you don't want to deal with this these values actually. You don't like to deal with this value because these are very complicated objects. So your idea is to come up with a signal processing algorithm. Now, if this is there, you're not going to calculate these objects. So then you want to go for certain simplification. Now, how would you simplify? Well, we'll look at the asymptotic regime. That's why high dimensional limits are quite important. But you have to remember that Beauty and the Beast, beautiful things happen, but the beast is also there. Okay. So typically we look for high dimensions, large dimensional, large sample size limits. I mean, that's quite natural. And there are so many theories for sigma equals I, null hypothesis. There are so many properties that you've already seen this thing, Wigner laws. And we call edges, that means the maximum and minimum eigenvalues. This Tracy and Widom laws are quite famous. Craig Tracy and Harold Widom law, 1994. They found what happened to maximum eigenvalue, the scaling limits, the scaling distribution of maximum eigenvalue, they found some time ago. So asymptotic spectral densities for sigma equals I, but sigma is not I. Sigma is not I actually. Sigma is not I somewhere here. This object is terrible. Like this object is terrible. It's very hard to deal with this one. But certain results have been derived by people over the last couple of years actually. So the most general form is like this. Any hypergeometric function PFQ. I mean, there are arguments here just omitted. So you are going to consider this kind of integral. So this integral is performed over unitary manifold. That means space of all group of all unitary matrices. And the answer turns out to be this kind of hypergeometric function of 2 matrix argument. For complex numbers, actually, this can be written as a ratio between 2 determinants thanks to Cat3. And again, this result was reinvented in 1989 by Grass and Richards in the Western world. Cat3 is from, of course, India. Quite famous. And PQ equals 0, not this P, okay? This PQ, I mean, they are not the same P. I'm sorry for using the same notation. When PQ equals 0, actually, so it's X and Zuber integrals, actually, or Harishchandra Itzhak Zuber result from theoretical physics, actually, in the 1980s, they found these answers. but there are no closed form solutions for R actually. There are no closed form solutions for R. And these forms are again not amenable to high dimension analysis. So if you want to do this kind of high dimension analysis somewhere here, I mean, these are going to be very, these are going to impede your development, and this is going to be very complicated object to deal with actually somewhere. So because of that, people have been working in this area for quite some time, and we have been also working in this area, me and my collaborators. So first one is myself, and Johnston is from Stanford, and Onatsky is from Cambridge econometrics actually. So we developed this in 2014 actually. When one of these matrices is rank 1, one of these matrices is rank 1, size rank 1, and then this one collapse to this result actually. The elegance of this result is, this is a combinatorial object like this. I have seen this is a combinatorial object. It's very complicated. This kappa is basically, you are going to sum over all partitions. I mean, these are very complicated objects. But here though, we could simplify and come up with a single contour integral. And you may say, oh, well, contour integrals themselves are complicated. Actually, it's not like that. So this is a scalar hypergeometric function, and this is a contour integral. So this is a contour that you take, you traverse to this contour counterclockwise. Now, the advantage of this contour integral is you can, if you want to do asymptotic analysis for some reason, high dimension analysis for some reason, you can easily use this very famous Laplace results and stuff like that. And you can easily get Laplace approximation, and you can do high dimension analysis. Actually, use contour integral itself. You can use apply Laplace approximation method. I mean, there are so many methods for asymptotic analysis of contour integrals. One of the methods is Laplace's approximation method, and there is a steep and descent method, and so on and so forth. So this is the advantage. Now you may wonder, I mean, these objects are again mathematics. No, actually, if you are solving signal processing problem, say likelihood ratio statistic that you are solving for particular detector to detect particular signal, actually you ended up with this kind of expressions, and then immediately you can come back to this kind of result and use some sort of tricks and circumvent the difficulties associated with the finite dimensional manipulation of this kind of objects. These kind of objects are very difficult to be manipulated. Actually. I mean, it's very hard to tackle down this kind of objects. So because of that, sometimes these alternative expressions shed some light into the development section. Now we are at the end of this talk actually. I was going very fast, probably you could not understand many things, or you think like, oh, still this is quite fairly mathematical. Not like that. People are, I mean, I have been working in this area for like more than a decade now. A fair amount of people, engineers, especially advanced signal processing engineers who are doing statistical signal processing, are working in this area. And if you look at advanced theoretical contributions and very practical implementations, actually heavily they rely on this kind of random matrices and stuff like that. Because of this, the result that I stressed out in the beginning, universality result actually. This universality actually, it starts from any arbitrary random measure, but ultimately converges to very simple probability model actually. So if you start with very complex interaction, as I said in the beginning, very complicated interaction among constituents actually, very complex mathematical equations. If you try to write Hamiltonians in complex systems, and you are not going to write it, or even if you write, it's very complicated. But then you can see eigenvalues of eigen instances, eigenvalues of these operators actually can be considered as eigenvalue spectrum from certain random matrix and symbols. So they made their life easy. And in the modern signal processing engineers, advanced signal processing engineers, and they also use this theory to make their life simple and come up with certain simple designs so that it enables faster connections, high throughput data transmission, and reliable communication. This is the most important thing that human civilization have been looking for. So with that conclusive remarks, actually, I finished my talk, and thank you very much for listening to me. I was going very fast, I believe, but I think first part was fairly accessible. I'm not sure about the second part, but thank you very much for inviting me to give this talk. And if you have questions, we can discuss. And thank you again. And over to you, Heshani. Thank you.
Thank you, sir, for that very informative speech. I think all you math enthusiasts gained some beautiful knowledge. Now let us move on to the Q&A session. As I mentioned before, you can direct your questions in the Zoom chat, or you can raise hand and ask questions.
There were some questions actually I can see. Can we have recording of this session? If you have any question, okay, then there was a question actually. Can please simplify things if you use orthogonal polynomials in page 45? Yes, you do. You do if you use orthogonal polynomials. You can simplify though. That is one of the most remarkable discoveries by M.L. Mehta, his orthogonal polynomial tricks, which was again used by Emery Teleta in his classical paper in capacity analysis of multiple antenna communication. Yes, you can. How RMT works in deep learning and interpreted machine learning. Yes, people are working along this topic actually. It's still at the research level. Not many success I have seen in the sense like deep learning, like there are hidden layers actually and hidden features. So can you explain it to a certain extent? People have been trying to do these things, but I did not see recently much success to say that, okay, you can interpret some stuff like that using random matrices. I haven't seen actually. So the next question is, what are the available implementations that support random matrix theory related calculations? Well, I think Professor Alan Edelman from MIT is a pioneer in this area. They have, I think, some sort of software support. I think his web page, if you go there, you can see how to do these calculations involving zonal polynomials and hypergeometric functions and eigenvalues and all sort of stuff actually. He used Julia language, I strongly believe. He has quite extensive material on his web page as far as I can see. So I lost these questions anyway now. Probably I can see.
Thank you, sir. The next question will be, are there any applications of random matrix theory in quantum field theories?
Okay, I'll talk to you like this because I'm not aware of quantum field theory. That I should confess that. But what I know is these people like Paul Wigner and everybody, they work in quantum mechanics, actually, not field theory. So I'm not aware of quantum field theory, but I know, which is related or not, I don't know. But the entanglement in quantum mechanics, there are certain entanglement actually, bipartite entanglement in quantum physics actually, quantum mechanics. There they use this so-called fixed trace ensembles actually they use to measure the degree of entanglement actually, bipartite entanglement. They measure using random matrices, but I would imagine that it's there, but I'm not aware of that. To be honest, I'm not aware.
Okay, sir. Thank you. The next question will be, matrices are just a quick way to solve equations. How come they are so important?
That's a very good question, actually. Quick way to solve equations. Yes, the Chinese people knew to solve simultaneous equations like that kind of couple of centuries ago, or probably 1,000 years ago. I can't quite remember these numbers. Yes. How come they're important? So actually, they are pretty important. Now, if you want to go to signal processing, advanced signal processing, and advanced any science advanced layer, if you go, so say for instance, like you want to study quantum mechanics, what Wigner found is found like certain symmetries are there. So the certain symmetries, Pauli matrices, using certain symmetries actually, then group theory kicks in, random matrices kicks in, group theory kicks in, and now huge masala is there, and now you are gonna derive insights using this random matrices. No, it goes beyond. Solving equation is the most fundamental thing that people have observed probably a couple of centuries ago, but we evolved from that point onwards, and now we know why they are happening, why the equations can be solved, why not solution exists. Not only that, the reason behind it, and if you randomize the coefficient, what will happen to the solution, stability, all the things we know actually right now.
One participant has raised his hand. Kamaluai, you can unmute and ask your question.
Yeah. So can we know that what are the available resources if we are going to study and participate into research in random matrix theory? What are the books, other resources, online lectures?
Yeah, so there are famous groups actually. Now the problem of this science is like some are fairly accessible, some material, whereas some material are not fairly accessible actually. Now you must have seen that towards the end of the talk, it's going to be highly group theoretic and stuff like that. Now, if you really want to understand this one, so you better check Professor Alan Edelman's webpage. because he is a person who can make very complicated topics very simple. Because of that, that group results are pretty good. But if you go to Maruna Deba and his group, actually, even they are working on signal processing algorithms, but they are pretty much into this high dimensional stuff and probably not much fairly accessible. But I recommend to study Professor Alan Edelman's group research and stuff like that, because that's fairly accessible for engineering students actually, because this is like applied point of view. We are looking at these problems. Yeah, that's my answer actually.
Yes. Thank you.
There's a one thing I can see here, like what if N and P, yes, infinitely nonlinear trajectories, my colleague Chaturangas, along nonlinear trajectories, P exponential, any relevant of, yeah, there are few results actually. There are certain results, but you ask very difficult question, because it's hard enough to solve this going along linear trajectories, actually hard enough, and going through nonlinear trajectories, yes, there are few results actually. Even there are results what happen when that goes to infinity, actually at the point of infinity, when it touches, what happens. There are generalizations, yes. Yes, another one actually say it is not related to RMP, how to find a well-separated p-points lie in n-dimensional sphere. Well, I cannot really answer your question exactly. When you say separated, actually you want to have sort of measure or metric to understand the separation actually. I would imagine that these results may be available in the literature, because I mean, there are something of sphere packing problems are there in the literature, and how you embed a few points on a sphere, actually surface of a sphere, so that the Euclidean distances among them is maximum. There's a sphere packing problem. Just double check that one, and probably it might guide you. How can you optimize the convergence rate of random matrix transformation if we want to find an optimal algorithm? Yes, these are pretty hard problem actually. Convergence rate of random matrix transformation. Yes. So sometimes this when you come up with it's like this, which I did not tell you, is basically when I say all these models converge to almost sure converge to non-random probability measure, actually I did not talk about certain restriction on the moments. Actually there are certain restriction on the moment, and there actually you consider the convergence in terms of O of square root of n, or O log n, or n to the power 1 plus beta is a non-zero value, and things like that. They consider actually this O values actually when it comes to the moment, like a restriction on this certain like kind of assumptions, which I did not mention. It could have been very difficult in that case. Yeah, there are stuff actually. I cannot give an answer. It's not like Maggie noodles. There are no 2-minute solution. Okay, so I cannot give you exact answer for this one. Yes, there are ways of tightening actually how to improve convergence and stuff like that. Yes, there are.
Okay, thank you, sir. The next question will be, it would be nice if you can shed some light into the connection between RMT and weight initialization in DNNs. That is, whether caving and lower random initialization techniques are mathematically rigorous or just empirical tricks.
Now I should comment here. I am not aware of this so-called DNN. I'm not aware of this thing actually. Random initialization mathematics. I'm not aware of this thing actually. Really, I'm not aware. So I cannot answer. But if somebody is here in this audience who do this this business DNNs actually, probably he can shed some light. But I am not aware of this thing really. As I said, I know very little about this subject. There can be many applications. If you type in Google like random matrices and something, you may find like hundreds of thousands of results, but I'm aware of very little. So according to my little knowledge, actually, I do not know anything like this. I'm sorry, but I do not know.
It's fine, sir. So the next question will be, what are the practical applications of eigenvalues in machine learning?
Well, when you talk about machine learning, it's like you can talk about learning theory. Machine learning consists of two parts. Learning theory itself is a theoretical subject, and outcomes that basically is algorithms. Okay. So you can deal with algorithms, say k-mean clustering algorithm, or like a support vector machine algorithm, or I mean, I don't know. There are so many algorithms. These are just Ross and Blight algorithm, or separating hyperplanes. I mean, there are so many algorithms. These are mentioning a few actually. But when you talk about algorithm, actually, you don't worry. I mean, if you want to learn algorithm, you don't much worry about what's happened probabilistically, what happened. But if you go to so-called learning theory, actually, learning theory, if you want to understand how the things are concentrated, like a concentration of measure theories and stuff like that, actually heavily depend on random matrices actually. Okay, eigenvalues of random matrices actually. So if you really want to dig into these details, how it happens, so you can check Stanford lecture notes in either electrical engineering or computer science department about learning theory, and they may have a very strong theoretical background. They will give strong theoretical background into learning theory part. So learning theory eigenvalues are pretty importance. But despite that, if you go to simple machine learning algorithm like dimensionality reduction, like part of multivariate analysis, like a factor models or principal components or canonical correlation analysis, if you look at, well, pretty much what you are doing is you are going to find low dimensional subspaces using this eigen decomposition actually. They are extremely relevant. And the PCA, studying PCA, they come up with the phase transition actually. So it is they are relevant in correlation, canonical correlation analysis and principal component analysis, as well as factor loading, factor analysis. But they may have different names in machine learning literature, but when it comes to the fundamental knowledge, these are pretty important, eigenvalues are pretty important. Now people ask, what are the present research, what are the fundamental mathematical areas we should be familiar with that is use extensively communication and signal processing. Now communication, Putha, if you take about communication signal processing, I would say statistical signal processing, because there are deterministic part of signal processing, filter design and stuff like that, and there's a statistical part actually. Now, if you look at communication theory, there is no deterministic and non-deterministic, but communication theory is how, I mean, in its core actually, in a sense, this is the fundamental question. How would you transmit a message from one place to another place or places reliably? This is the question even Shannon tried to answer long ago actually. How do you establish reliable communication? Now, when you say reliability, you have to talk about reliability because it's not reliable. Since it is not reliable, why? Because of noise. Because of that, noise is a random process. So the most important thing I have seen is linear algebra and random process. If you want to learn communication theory, communication, do research in communication, linear algebra and random processes. And signal process, statistical signal processing, again linear algebra and random processes. Now you can see they are interwoven actually, communication, signal processing, because communication is part of signal processing, although I mean they develop independently more often, but communication theory, if you want to learn extensively research in communication theory, or if you want to study communication theory, what you need is random processes and linear algebra and bit of integral transforms. Signal processing literature the same actually. Not much difference. Of course, you are supposed to know complex numbers. You're supposed to know complex numbers. So somebody asked, can we have dimension reduction in high dimension? The PCA fails in high dimension. Yes, it does. It does. Because PCA fails in high dimension. I did not talk about eigenvectors actually in this talk. Actually, eigenvectors also have phase transition. Like a below certain threshold, like cosine value below certain threshold actually, you can't identify certain eigenvectors. They are uniformly distributed over certain sphere, but above phase transition actually they are confined to a certain conic structure is there. So you know that it is confined to cone, but in other cases actually you don't know where it is. So this phase transition happens actually in high dimension. That means basically eigenvector principle sample component eigenvectors do not represent population eigenvectors actually. It happens. The gap is pretty high actually. And we can bring it down to low dimensional problems where classical statistic estimation can be used. Well, typically if you use principal component analysis, what you do is like you try to find low dimensional subspace. So you are gonna project the original data cloud onto the low dimension subspace. The advantage is dimension to reduce, and then you can do mathematics there. But the thing is like then you cannot go back exactly, because when you project onto low dimension subspace, you're going to lose something. The very essence of PCA is you make sure that the information that you are going to lose is as minimum as possible. That's why you minimize the variance subject to certain criteria if you study theoretical. So you find the highest variance directions for some reason, and then you project onto that directions actually. So you are going to lose some information. Can't do much about that. What are the applications of RMT related to game theory and reinforcement learning, I suppose? So the learning theory, random matrices are heavily used in learning theory, but game theory I am not aware of. I mean, I'm not expert in game theory. I know only very simple things and Nash equilibrium and stuff like that. So what I can see is like this. In game theory is kind of I don't know, I think it's kind of sort of optimization problems are running. Now, if you optimization, there are deterministic problem as well as stochastic problem actually. Now, when it comes to stochastic optimization problem, say for example, the well-known stochastic optimization problem is capacity analysis of multiple antenna communication actually. Capacity, and we call it ergodic capacity. Ergodic capacity is expected value of log of determinant of some matrix actually. So when you try to analyze that one, expected value of log of determinant. So if you want to take expected value and then you have maximization, power maximization. So this is called Shannon capacity actually. So this is basically a stochastic optimization problem. So to find the correct answer there, or find a proper power splitting algorithms, actually heavily people use random matrices as far as I'm aware of, but I don't know about game theory actually to comment it. Sir, can you comment on the connection between RMT and convex optimization? Now, I think, I don't know, Dr. Chaturanga, are you there? I can remember Dr. Chaturanga was here. Are you there? He was here, I think.
Hello, you can hear me?
You are here. Okay, Dr. Chaturanga, you are the expert in optimization. I'm not. Now, this kid asked, what are the, can you comment on the connection between RMT and convex optimization? So, well, I think I would say like this, RMT and non-convex optimization, I would say, because if you consider maximum eigenvalue problem, it's like a two-norm calculation. The problem is not convex, right, Chaturanga? I don't know, probably he cannot hear me here. But I would say random matrices and more often non-convex problems actually. Some problems are not convex either. They are non-convex actually. There should be connection, but I don't know. Dr. Chaturanga, are you there? Can you comment? Probably disconnected. Probably I am not there. I don't know. Probably I'm not there. Can someone hear me?
We can hear you, sir.
Yes, sir.
Oh. So I was waiting Dr. Chaturanga's opinion on this matter because I think he's speaking, but we can't hear Chaturanga. So it's pretty bad link. I don't know whether you guys can hear. I can't hear.
His voice is breaking, sir. We can't
Yeah.
also hear.
That's what I told you. The idea of communication theory is to establish reliable communication between two parties. Now you can see the meaning of reliability. You experience now reliability. That's the idea of communication theory. Because of non-reliability, you need to have that theory. That's pretty much what I can tell about convex optimization and RMT actually. You may be using RMT techniques in convex optimization, but some problems in random matrices theory, they are not convex at all. Very simple logic is to find the maximum eigenvalue problem actually. It's called Rayleigh quotient. Rayleigh quotient maximization problem is basically it's not a convex problem. It's a non-convex problem, but you have a closed form solution. If you guys have any more questions.
Seems like the participants have asked all the questions.
Oh, that's great. Thank you very much.
Let's move on then. Thank you, sir. First of all, thank you for those very insightful answers. And thank you again for joining us today to inspire these young enthusiasts and expand their horizons. The blessing of high dimensionality, a random matrix theory perspective. The third M Talk, organized by the Mathematics Society of University of Moratuwa, has come to an end. We invite you to join us with our upcoming M Talks as well and gather more meaningful experience just like today. Also, follow us on social media and stay tuned for our next update. Until then, be safe and have a nice evening.